we have to get into the mathematical formulas. Our product of f and g is equal to its real part number minus its conjugate divided by 2i. And in this case, the inner product of f and g, by the inner product axioms, the conjugate of an inner product has to be the reversed inner product of g and f, over 2i squared. And now here's the nice part. Because of the way f is shaped, its inner product with g is going to be equal to the x operator multiplied by p minus the p operator multiplied by, that's the commutator. And the way, if we just reflect these, you get position multiplied by, actually no, I think this should be this way and this should be that way. Operators don't commute with each other, but scalars like these guys do. Well, this is actually a vector, but this is scalar. Wait, no. Momentum is a vector, but vectors commute with each other, operators. And when you subtract a from b, you get the commutator of x and p. xp minus px. How do you even deal with this? Well, here's the nice thing. P, the operator, has a very quick definition. And so, when we plug it in here, what does it do to a test function? Well, let's take x hat p hat minus p hat x hat and apply it to a poor unassuming function right here. F plus, this time you take x d dx f by the product rule. And so this cancels out with that, and you get minus h bar f over I, and minus 1 over I is just I. So you get I h bar f, which means this operator, since this is equal to I h bar f, this operator is just a scalar, I h bar in the end. Which is cool, right? Because when you cancel out the i's, you're left with the fact that, plugging back in here, the standard deviation of position multiplied by the standard deviation of momentum squared has to be greater than or equal to h bar over 2 squared. The standard deviation has to be positive by definition. This is positive, so we are legally allowed to take off the square without adding a plus minus, and get the final statement of Heisenberg's true uncertainty principle.